Alright, and welcome to our lesson for section 10.5 over what are called tangents. You might remember the word tangent from when we talked about sine, cosine, and tangent from trigonometry. It's not exactly the same thing here. We're talking about a line called a tangent line when we refer to circles. So we'll explain what that is here in just a minute, but they have a lot of applications in geometry and then further on in other mathematics, and so we'll look at the introduction of what they are and how they affect circles right now. So you'll notice these two boxes are for the vocabulary terms tangent and common tangent, and then we'll talk about what a point of tangency is. But if you have not filled these out, make sure you look in your textbook and find those definitions. We're going to talk about those next. Alright, we have a tangent, which is a line in the same plane as a circle that intersects a circle at exactly one point. The underlined part is the main part of the definition I want you to understand. Any line that only touches or intersects a circle at one point is called a tangent. And that point where the line touches or intersects a circle is called a point of tangency. So we would say that line AB is tangent to circle C at point A. And then a common tangent is a line, ray, or segment that is tangent to two circles in the same plane. So in both cases, line L is tangent to both circles. It's a common tangent. And so we're going to look at how to draw or how to identify common tangents. If there isn't a common tangent, we would write no common tangent, and that is possible in certain instances. So remember, common tangents are lines or rays or segments that are tangent to two circles in the same plane, this piece of paper being that plane. So for example 1a, we would just want to line up a line using a straight edge that would touch both circles. I don't want to draw through the circles because that would intersect at several points. I want to do it so that my line just touches both circles, but does not go through them in more than just this one point here and one point there. So there's a common tangent, but we also could go to the other side and get another common tangent. Okay, let's turn it the other way around. Might help you see it better. We're going to connect these two circles with that tangent, lining it up so that they just touch. Okay, so there's another tangent line to both circles. Common tangents could look like that. If you look at part B, if I draw a tangent line to any point on this bigger circle, a line that only touches the tangent once, if I go like that, it goes through two different places. You'll notice that I cannot draw that tangent line also tangent to the other circle. When you have concentric circles, there is no common tangent. All right? Anytime one circle exists in the interior of another circle, but does not intersect the other circle, then there's not going to be a common tangent. But if they are completely separate circles where they do not intersect, they can still have common tangents. As you saw in this example, there's one. Okay, any line that would touch this circle at one point and this circle at a different point, that's a common tangent. But we could have another common tangent if I go the other direction. There and there. Okay? And now when two circles only intersect each other at one point, we can say that the circles are tangent to each other, or tangent circles, and there is a line of tangency that in this case is going to be vertical, because I could draw the centers collinearly here, horizontally, and so this line of tangency is vertical, because it only intersects each circle at that one point. So that's your line of tangency. So usually we will have two common tangents. Sometimes we only have one common tangent, and other times there are no common tangents. All right, for two given circles. So let's take a look at our first theorem here, and that is the relationship of a tangent line to different parts of the circle. Now, if we have a plane and a line is tangent to a circle, that is only true if it is perpendicular to a radius. And all that really means is anytime we have a tangent, I can draw a radius to that point of tangency that will always be perpendicular. And this idea that this tangent line is always perpendicular to a radius comes into play in a lot of different things, and we'll look at a lot of different examples in class that illustrate that a lot better. But these will always be perpendicular. Okay, if I move this point of tangency, let me just turn it like this. If I move that point of tangency, the radius that is perpendicular to it turns with it. So you can see that moving, okay, like that. Okay, so it's not super important that it's always at the bottom. It can be in a lot of different places, but as this point of tangency moves, that radius will move around with it. So let's take a look at our first example. Example 2a. We are given that KL is a radius of the circle, and we want to determine whether or not this actually is a tangent line to that circle. It looks like it only intersects at point L, but to verify that, we're going to go back to this principle. If this is really a tangent line, that has to be a right angle. So as I've drawn it here, where the radius is 20 and then from K to M is 29, I create a triangle. If this LM segment is actually tangent to the circle at L, this must be a right angle, which would make it a right triangle. If this is not a right triangle, then this cannot be a right angle, and that means that these are not perpendicular, so that's not tangent. There's a lot of justification I went through with that, so we'll write that out as we go. So all we're really doing in this problem is checking to see if this is a right triangle. Okay, we're checking a squared plus b squared to see if it does in fact equal c squared. Remember, the longest side has to be the hypotenuse. We're looking to see if this is your right angle at L. So we're just going to plug in 20 for A and 21 for B and see if that equals 29 squared. So let's do some calculations. 20 squared is 400, 21 squared is 441, and 29 squared is 841. So if I add these two, 400 plus 441, that is 841, which equals 841 on both sides. So this is a right triangle. Since triangle KLM is a right triangle, angle L is a right angle. Therefore, KL is perpendicular to segment LM, so segment LM is tangent to circle K. That is our justification. We've shown that that is a right triangle, so that means that they are perpendicular, which makes it tangent to K by this theorem. All right. I want you to try and do part B using the same process. We're checking to see if this is a right triangle, and then write your justification the same way to see if that works. So again, you're checking Pythagorean theorem. In a right triangle, a squared plus b squared equals c squared, so we're checking to see if 14 squared plus 16 squared does in fact equal 21 squared. Okay. If not, then you can immediately say that this is not tangent because it doesn't form a right angle. All right, pause the video if you need a little more time, which you probably will, to work this out. But this is what we should get. All right, when we work this out, we get that 452 is what we get on the left, and 441 is what c squared is. Those are not equal. So this is not a right triangle. So you would write triangle XYZ is not right. So XY is not perpendicular to YZ. Since these aren't perpendicular, it cannot be tangent to circle X. All right, example 2 is a little bit different. We don't have to do quite as much justifying. If you look at example 2, we are told that WE is tangent. We know that to start with. That makes this a right triangle. So Pythagorean theorem does have to work in this problem. We're not guessing and checking. We're not trying to verify that it is. We know that to begin with, but we are finding the value of x, which is the radius of your circle. From D to W is x. From D to this point is x, and then from that point to E is 16. So the total length of DE would be expressed as 16 plus x. Not just 16, not just x. Okay? So what we have to do is check Pythagorean theorem, or plug it into Pythagorean theorem to help us solve for x. You need to understand what A is, what B is, and what C is as it relates to this. A can be called one leg, which would be this side, x. B can be called this other leg. And C is this combined part making our hypotenuse. So we would express that as 16 plus x. Okay? And so we're going to plug these parts in here. We're going to have to do a little bit of algebra to remind ourselves how to do this. For A, it's just x squared. Or for A squared, it's x squared now. B is 24, so the next part is 24 squared. Now C squared is this. I'm going to help you out a little bit with this, and we'll come back to look at how we got that in class, but I won't take up a lot of the video time to show you that. This side I'm going to simplify for you a little bit. X squared plus 576 is equal to 16 plus x squared is not just 16 squared plus x squared. You would have to do FOIL here, and in that case I'm going to rearrange it for you, but I want you to write this down. We'd have x squared plus 32x plus 256. Okay, I've done a lot of that, and I'll explain how I got that later on, but right now just make sure we have that written down. There's a lot of algebra involved here, but I do want you to notice that both sides have an x squared. This becomes a whole lot easier because I can cancel those out. If I subtract x squared from both sides, those cancel. So I don't have as difficult of a problem as I used to. The numbers are still big, but I don't have an x squared. Now we just solve for x. Subtract 256 first. And this side becomes 320 equals 32x. So we just divide by 32 both times, or on both sides I mean. 320 divided by 32 gives us that x equals 10. And that is the answer to our problem. It says find the value of x. Okay? Alright, that leads us to our last theorem and our last examples. If we have two segments in the same exterior point intersection here, so let me say that differently. If I have two tangent segments that intersect at the same point B, and they're both tangent to the circle, they have to be congruent. Okay, that's just a rule that we're going to notice. So we're going to use that to help solve some problems. So here we're told that AC and BC are both tangent to circles Z. So to find the value of x, you just need to recognize that these have to be congruent segments, so these are equal. So we just set them equal. 4x minus 3 equals 3x plus 2, and we solve for x. 4x minus 3x is x. The only thing left on this side is 2. Then we add 3 to both sides. In this case, x is 5. Okay? We're going to use that same idea to help solve some parts of this example. Okay, we want to find the perimeter of triangle QRS. In order to do that, I need all these little pieces. And so I want you to look at this. QN and QL have to be congruent because there are two tangents that intersect at a point outside. Okay, so we're told that QL is 2 centimeters, so QN is also 2. Okay, that means the entire segment QR is 8. Well, remember that if QL is 2 and QR is 8, I would do 8 minus 2 and get 6 centimeters for LR, which has to be congruent to MR because they are both tangent to circle T at points L and M. So that's also 6. SM is 10, so SN is 10. So I have 3 sides to my triangle. 10 plus 2, which is 12, 8 for this side, and 10 plus 6, which is 16. So the perimeter of the triangle is the sum of those 3 sides, 12 plus 8 plus 16, which is equal to 36 centimeters. And that concludes our notes for this lesson.